and I just posted the three statements that they're talking about here. So they're talking about intermediate value theorem, they're talking about mean value theorem, and they're talking about extreme value theorem. So we're going to go through each one of these theorems, and we're going to get the idea of what each one of these says. And the picture says everything for each one of these three. So let's go through the first statement. So it talks about the intermediate value theorem. By intermediate value theorem, there is a value c on the interval 0 to 3 such that f of c equals 10. Now, let's go through the general intermediate value theorem and investigate whether this statement is true for the function they're talking about, because they say let f be a function with selected values over here. And then, so again, let's go through the general. So the general, forget about this problem. Let's just think in what's being said here. So here's my graph. I don't know. Here's some x and y axis. And then, I don't know. I have, here's y, x. And basically what it says is that it's continuous from A to B, including on A and including on B. So my function is continuous all in between here. There's no breaks in it. And n is any number between f of a and f of b. So let's say this is f of a. And let's say up here is f of b. So now I have some idea of what's happening here. So I have that this is a point on my curve, this a comma f of a. And then this is a point on my curve, b comma f of b. Now, the thing is that I needed that f is continuous. Because now, in any which way I go from here to here, right? And any which way, okay, so let's say this could be my curve. It has to be continuous. That's what's key. So I could have drawn it like that, but I could have also drawn it equally as well like this. Right? Or I want to make it look like a function. That's not a function. This is a function. Right? I could have done that. Doesn't matter as long as it's continuous, right? And it's a function. Okay, but yeah, continuous. Okay. So now what I have is between f of a and f of b, there's a whole wide range of numbers. But for any number n, there has to be some number c, right? So if you go across at n, there's some point right here. There has to be some c between a and b with f of c equal to n. For any number. So, okay, suppose that f is provided f is continuous. Okay, and n is any number between f of a and f of b. So I have this, right? I don't know anything about f. You see, f could be, it could be a straight line. It's continuous if it's a straight line. It could look like anything as long as it is continuous. And this is some n over here, right? It doesn't matter. Any n between, then you know, you go across, you can find out where it is. You go down, and there has to be some c with f of c equal to n. Now, what's key in this is that f needs to be continuous. So if you look, right, if you look, and it just says f is a function. So can I apply the intermediate value theorem? I cannot, because I do not know if f is continuous on this interval. If I were given, so this is not, I cannot, this is not necessarily true. But if I were given that f is a continuous function, let's see if this first one would be true. Okay. So if let f be a continuous function, now let's investigate. It's not true, because if we're gonna use, oh sorry, I'm circling the wrong thing here. Sorry, hold on. This is not what I meant to circle. I meant to circle that f needs to be continuous. Okay. So f needs to be continuous. I apologize. So we have, Okay, so f needs to be continuous. That's key. Otherwise, it could look like this, right? And I could possibly skip a value, right, like this. Okay, and then there'd be some n right here, right, where there's no c value, right? It's not defined, and it could be whatever. It could be defined up here as a, and then there'd be this n value that would not make the intermediate value theorem true, right? If n is any number, then there could be a number if it's not continuous, because you see here, this function isn't continuous. So you need continuity to apply the intermediate value theorem. You need to guarantee that the function is continuous. In this case, it doesn't say that. But let's imagine that we did say that. Okay, let's imagine that they did say that f is continuous. And let's see how that changes. Let f be a continuous function with selected values. By intermediate value theorem, there's a value c in the interval 0, 3 such that f of c equals 10. Well, let's see. This is talking about the interval 0. So let's say a is 0. So let's change our general to a particular. And then the b value is 3. And we want to see if there's an f of c value equal to 10. Well, what's f of 0? F of 0 is 15. So this, okay, so let's try and get these things out of here. Okay, there we go. Okay, and let's say I had, so f of 0 is 15. So then that means that this value over here, let's change our color. Let's say that this is 15. Right, so that's a point right there on my curve. And then f of 3, right? So I want to investigate on this interval. F of 3 is then 9. So let's say 9 is over here. Now this is 9. And this would be, forgetting about, this is 9. Now, is there guaranteed 10 is here? How could I go from 15 to 9 without crossing 10 in a continuous way? I would have to cross 10. And there'd be some c between 0 and 3 with f of c equal to 10. Because this point, f of c would be 10 along here. Okay? That's if I know f is continuous. But I don't know f is continuous, so I can't say that the first one is true. Now, let's look at the second statement. By mean value theorem, there is a value c in the interval 0, 3 such that f prime of c equals -2. Now, let's draw a picture, and let's do the same thing again. Let's get the general idea here. Let's say that I have some function. And this one, it's a little bit more of a complicated geometric argument than intermediate value theorem, but we really see it when we have a picture. So we need again that we need it to satisfy certain hypotheses, right? So here's A, let's say again, and then let's say here's B, and now so here's B, I don't know, some other point, and then this is gonna be f of A, and then this point over here is gonna be f of B, and what I want to show here is I want to show what this is. So basically first, f, like in the last one, it had to be continuous. So right away we should start, seeing what's happening over there. But let's just first focus on the general idea. So it's got to be continuous, okay? Then it's got to be differentiable. Now, differentiable, another good way to think of differentiable is to say smooth. So smooth, let's do this in a smooth way. Say something like that, right? That's smooth. I moved continuously and smooth from A to B. Now, what the theorem says is that there must exist this here, right, f prime of c, there must exist a c where the slope of the tangent line to this curve is equal to the slope of this secant line. Because what is this? This is the slope of the secant line joining a comma f of a, that line right there. So let's look at this geometrically in the picture that I drew. So you guys should see that that line that I just drew is the secant line joining b comma f of b and a comma f of a. Okay, look, y2 minus y1 over b minus a. That's the slope of this secant line. And what the theorem says is that if it's continuous, if you look at the tangent line, there must exist some point C with, must exist some C where the tangent line is parallel or the slopes are equal. If you look at that line right there at that point, I tried to do it as best I could, right? This line, I'm trying to make it so it's perfect. So if you look, these two lines have the same slope. So this line right here, right? That, what's f prime of c, the slope of this line, right? That's the tangent line. F prime of c is, again, slope of tangent line. And this here, this formula on the right-hand side is slope of secant line. And what the mean value theorem states is that if f is continuous and differentiable between a and b, so it's smooth and continuous between a and b, the slope of the secant line, okay, has to have some matching, there must be some point c where the slope of the tangent line at that point, c comma f of c, right, that's the point c comma f of c, the slope of that tangent line is going to be equal to the slope of the secant line. That must exist provided f is continuous and differentiable on this interval. And if you look, okay, there, again, you need continuous. And it does not say that f is continuous. So 2, you cannot conclude. And then now in the last one's the easiest one, it's the most intuitive. It basically says that if f is continuous on any interval, then there must be a maximum and a minimum on that interval. That's it. Okay, so any function, just imagine anything, right? Like there's a few pictures here. This is some function. This is the interval a to b, right? There must be a maximum. That's the max. That's the highest it goes. And then there must be a minimum. That's the lowest it goes. Okay, same thing with this one. It could be that the minimum's at the endpoint or the maximum's at the endpoint, but here this is the maximum, right? This point right here. And then there's a minimum. Always, provided f is continuous. And if you look at this one as well, like, you know, you can see that it says f, it has to be continuous. So it's not 3 either because you don't know if f is continuous. So the answer in this case would be none. But let's just go through this example again with mean value theorem and extreme value theorem, because I already came up with a hypothetical. So let's say f is continuous. Let's say all we have is f would be continuous. Let's look at statement 2 again. If f is continuous, then I should, well, all I know is f is continuous. So can I apply the mean value theorem? No, because I would still need to guarantee that f is differentiable. So if all I knew was that f is continuous, I still wouldn't be able to apply the mean value theorem because I don't know about the differentiability of f. So let's now say that f is continuous and differentiable. And let's evaluate what we have for statement 2. Okay. Now, by mean value theorem, there's a value c in the interval 0, 3 such that f prime of c equals -2. Well, now, what takes the role of a and b in this case? Okay, so the role of a and b in this case are now substituted by 0 and 3. So this is 0, this is 3. And then this value over here we just saw was 15, but I'm going to erase all this stuff here. So let's see if I can get rid of everything at once. Nope, nope, that's definitely not what I wanted to do. Alright, let's see if I can do this. I think I can. Oh, not that much. Let's see. Okay. I do not want to delete that. Okay, and then I'll just let's see how I'm gonna do this. Okay, so let's just see. Let's just now do another graph. So now just ignore. Let's see what we have. So now in this case, I have it where the role of A is 0, and they tell me that f of 0 is 15. So I have this point, 0, 15. So that's a point. And then they tell me that the role of, so this is 0, and then the role of B is 3, and they tell me that f of 3 is 9. So let's say, I don't know, right here. Here's 9. And then that's a point. And now I'm pretending that it's for sure the case that f is continuous and differentiable. So now I'm going to draw some curve. And that curve just has to be continuous and smooth. Okay, so something like that maybe, let's say. Okay, who cares? Okay, now what the mean value theorem states is that the slope of the secant line joining these 2 points now, let's say this line, this is going to be the secant line. That's the secant line. Okay, there has to be some point C. And they tell me they want to find out. Okay, so what is the slope of the secant line? Right? What is the slope of the secant line? Is there a derivative? If whatever the slope of the secant line is, there must be some C where the slope of the tangent line matches that. And I'll try my best to find out where that is. So that's probably maybe somewhere like over here, looking something like that maybe. There could be more than one, but there's at least one. So I'm going to try and do it. So here, I just take this, move it, maybe somewhere over there. There we go. Okay. And then that's the tangent line. And then this point right here is C. Right? So we can see that then there is some f prime of C equal to the slope of this secant line. But in this case, right, what is the slope of that secant line? Well, this point right here is 0, 15. So it's 15 minus 9 over 3 minus 0. And, or over 0 minus 3. Good. Okay, 0 minus 3. I apologize, I switched up those two. 6 over negative 3 is then negative 2. And there would have to be some f prime of C equal to negative 2. So if I knew that f were continuous and differentiable, then 2 would be true. And now the question is that let's do if we knew f were continuous and there is a value c in the interval such that f of c is less than or equal to for all x. Yes, this is saying that there would be a minimum. This last statement is saying that there would be a minimum on that interval. There'd be an f of c value that's less than or equal to all the other values, which is true. There's always going to be a minimum. Like in this case, look, that point right there is that f of d, right? F of d is less than or equal to f of x for all the other x on this interval. Look, you could find any, you could go all throughout here. You're never going to find an x less than f of d on that interval. So extreme value theorem would be true. All of them would be true if I knew that it was continuous and differentiable. If I knew it were just continuous, then 1 and 3 would be true. And if I know it's continuous and if I know it's continuous and differentiable, all 3 are true. If I know it's just continuous, 1 and 3 are true. And if I know nothing about f, I cannot guarantee any of them being true. That's why the correct choice was none, because it did not tell me anything about f being continuous or differentiable.